If 3, 2, 1, and we're live.
Well, good evening, everyone. Welcome once again to Amateur Astronomers Incorporated, also known as AAI, for weekly Fridays at home presentations. AAI makes its home at William Miller Sperry Observatory on the campus of Union County College in Cranford, New Jersey. And since the observatory is closed at this time, we're continuing to hold our weekly presentations online like this. Our presenter this evening is AAI member Dr. Al Gottlieb. Dr. Gottlieb received his undergraduate degree from Stevens Institute of Technology. He received a master's from Brandeis University and received his PhD in experimental solid-state physics from Brandeis University. He worked at Bell Labs for over 25 years. He taught at Seton Hall University and at NJIT and also at Union County College. So the title of his presentation is The Implications of the Cosmic Silence, or So Where Is Everybody? So with that, Al, please take it away.
Okay, well, I'm here in West Virginia, not with the telescope in the background. You can see it, looking for aliens, but we'll talk about this. So what I want to do with this talk is make a short presentation, if I can, say 20 minutes or so, and then I want to open it up to discussion. And just make a note, by the way, this is a new subject for me, so I would like to hear from you and what you have to say about this topic. I'm a little discouraged, but let me go through some things and some of the history of our looking for technology life outside of our solar system. And so let me just go with this. So the universe is incomprehensible vast with billions of other planets, circling billions of other stars, and there should be life forms on other planets going around other stars, and there should be lots of these. And the question is, why haven't we been contacted? And I've been wondering about that, and I'm not the first one to ask. 1 second, I'm having trouble with my going forward 1 minute. Why my slide doesn't want to go forward. Okay, so where is everybody? And there's a paradox that was asked by a famous physicist, Fermi, who wanted to know. He was at a meeting in 1948 and asked the question of other physicists, you know, if there are so many stars and the stars must have planets and there must be life on those planets, why haven't we been visited? Okay, and so I'm going to go through some of the people who looked for this, and what propelled me to do this talk was there was a paper by Daniel Whitmire, and he's a retired astrophysicist who teaches mathematics at the University of Arkansas, and once thought the cosmic silence indicated we as a species lagged far behind everybody else. And he has come to some other conclusions, and not the happiest of conclusions. So let me, 1 second, go here. I have why my mouse is not going forward. I will do this manually. 1 second. So where are they? So during the summer visit to Los Alamos Science Laboratory, most likely in the 1950s, Enrico Fermi is said to have asked the famous titular question of this article. The setting was a luncheon with colleagues Immanuel Konovsky, Edward Teller, and Herwood York, no small people in the field of physics. And Konovsky later recalled that on the walk to lunch, the four had bannered about a New York cartoon depicting aliens stealing public trash cans from the streets of New York. And in the middle of lunch, Fermi suddenly returned to the topic of aliens by asking his question. he was expressing his surprise over the absence of any signs for the existence of other intelligent civilizations in the Milky Way. And in this, by the way, what we're talking about is civilizations that can communicate with light or radio waves. They're the same. Light, radio waves are a form of light. And so it's a technology in which the civilization has reached a point in which they can communicate with electrical signals. We did this in the 1900s, and matter of fact, in 1903, it was the first communication between the Western Hemisphere and Europe was done. And so our civilization, so to speak, in that textural way is roughly, we're 100 years old. And so the universe is, okay, we did this one already, I'm sorry. So the first way that someone wanted to analyze this, and this is a famous, the Drake equations, I don't know if anyone's heard of this, but it is a probabilistic argument used to estimate the number of active communicative extraterrestrial civilizations in the Milky Way. And I apologize, but I'm going to put the equation out and with all the parameters. It's a simple equation. The equation was written in 1961 by Frank Drake, not for the purposes of quantifying the number of civilizations, but as a way to stimulate scientific dialogue at the first scientific meeting on the search for extraterrestrial life, SETI. And there's a talk that's going to be given on the 29th, and our club people can actually join it from the, the Dark Skies talk out of California on someone talking about SETI. And the equation summarizes the main concepts which scientists must contemplate when considering the question of other radio commutative life. And it is more properly thought of as an approximation than a serious attempt to determine a precise number. So just to say, what is the number? Is it, 5, 1,000? Can we put a handle on how many active civilizations should be out there that would be able to communicate with us? So Drake hosted a search for extraterrestrial intelligent meeting on detecting radio signals. And the meeting was held at Green Bank facility in 1961. That was before the telescope behind me was built. He had a much smaller telescope, but he actually started to look to see if he could pick up radio signals from other life forms that had the technology to communicate with sending radio signals. And the equation that bears Drake's name arose out of his preparation for this meeting. Okay, and here's the equation. You will not be tested on it, or maybe you will be in our break. But the equation says the number of active civilizations that can communicate with us with radio signals or light signals or whatever that we could pick up, most likely radio signals, because we are very have radio sensitive antennas for that, has a number of dependencies. One is the average rate of star formation. So you need he said you need a star that will be forming so that you can get a planetary system. The fraction of those stars that have planets, okay, the more stars that have planets. And when he did this in 1961, he didn't realize that what we're finding is most stars do have planets. The average number of planets that can potentially support life per star that has planets. So that's your NE over here. And that's planets that are in the Goldilocks zone, so to speak. The fraction of planets with life that actually go to develop intelligent life, okay? The fraction of civilizations that develop a technology that release detectable signs of their existence into space. And L is the length of time for which such civilizations release detectable signals into space. Okay, so that's the Drake equation. It's not meant to be an exact equation, but if you look at it and put in finite numbers for everything, you come out with the conclusion that we should have many civilizations that are accessible that give out signals. And here's some of the numbers that Drake used in 1961. He said, you know, on average, there's one star per year produced in the galaxy. 1/5 of, or to half of those stars have planets. We know that it's merely probably more than half. And 1 to 5 stars with planets will have the 1 in 5 planets capable of developing life. And so 100% of these planets will develop life, and they will develop intelligent life. And then he says, what percent would be able to communicate with us? And he guessed between, you know, 10% and 20%. And then he guessed, what is the lifetime of this technologically civilization? And he came up with a number between 1,000 and 100 million years. Okay. And with those numbers, he estimated that minimum we should have at least 20 technologically advanced civilizations that can communicate with us, and at the maximum there should be at least 50 million planets out there sending out radio signals to us. So there should be a finite number of people out there, or I wouldn't say, we'll put quote people, life forms that are technologically advanced, that they can generate electromagnetic signals that could be detected by our antennas on this planet. Okay, not so they're not even saying that they have the technology to send a spacecraft from their planet to visit us, but that they will be sending out radio signals and that we should be able to detect. Okay, and the question is, okay, so this should be, and so Drake states that given the uncertainties, the original meeting concluded that n was properly equal to the lifetime of the technologically our organism that was producing radio signals, and so there would be probability between 1,000 and 100 million planets with civilizations in the Milky Way. Okay, so there's no reason why we should not detect them. So the lifetime of a civilization within it communicates its signal into space as L. And so some other people started to look at this, and Michael Shermer estimated that L is 420 years, based on the duration of 60 historical earthy civilizations. Using 28 civilizations more recent than the Roman Empire, he calculated 304 years for modern civilizations. Doesn't give me a lot of confidence. There's some arguments. It should be also argued from Michael Shermer's results that the fall of most of these civilizations was followed by a later civilization that carried on the technologies. So it is doubtful that they are separated civilizations in context to Drake's equation. So like if the Romans invented radio, then when the Roman Empire fell, those empires that came into power would use that technology. And so even though the Roman Empire was only lasted for whatever 1,000 years, it's been 2,000 years plus since the Roman Empire. And so that civilization would be over 2,000 years old. In the expanded version, including reappearance numbers, this lack of specificity in defining single civilizations that matter for the end results, since such civilizations turnover could be described as increasing the reappearance number rather than increasing L. And so L would be a bigger number. Okay, so there's one. David Grinspoon has argued that once a civilization is developed enough, it might overcome all threats to survival. It then lasts for an indefinite period of time, making the value of L potentially 1 billion years. Just a caveat, you know, how much longer does our life on Earth, can it be around, based on how long will the sun live? And the estimates are somewhere in the order of a couple billion years, 2.3 billion years. In 2.3 billion years, even though the sun's not going to die, it's going to get hotter and it'll be more difficult for life to survive on this Earth. But so we still have a couple billion years to live on this planet before the sun starts reaching its end phase. matter of fact, the sun has another 5 billion years before it's going to eventually be turned into a red giant. But so we do have several billion years on that end. And the astronomer Carl Sagan speculated that all the terms except for the life of the civilization are relatively high, and the determining factor in which there are large or small numbers of civilization in the universe is civilization lifetime. So Carl Sagan speculated that it's the civilization lifetime which is the most important aspect. And what was interesting, and from the Drake equation, Sagan was strongly motivating factor for his interest in environmental issues and his efforts to warn against the dangers of nuclear war. Okay, so he felt that nuclear war could end our civilization, which is absolutely true. But however, there's another one that could do that, and that is climate change. So there are the two possibilities. So let's go on now for what motivated me. So implications of technology species being first and early by Daniel Whitmire, and his paper is in the International Journal of Astrobiology. So from his paper, he says, I taught astronomy for 37 years. I used to tell my students that by statistics, we have to be the dumbest guys in the universe because we haven't found anybody. That's what he thought. By the way, it's probably Mark Twain, but someone said it's not Disraeli, that said there's lies, damn lies, and statistics. But anyway, but that's an off thing. So after all, we have only been technology for about 100 years, while other civilizations could be technologically advanced, more advanced than us by millions or billions of years. So they really could be very advanced. And so, we're just babes in the woods, being roughly 100 years old. Recently, however, he changed his mind by applying a statistical concept, and I'll go over this a little bit. That was the first I've heard of this, the principle of mediocrity. And you go, well, hold a second, what's this mediocrity? The idea that in the absence of any evidence to the contrary, we should consider ourselves typical rather than atypical. That's very important. So one of the people were saying that the reason there's not other life forms that have contacted to is that we are very atypical, that the probability of life is forming is extremely small. And what Whitmire is going to say is that's not the case, that we're really typical, and that life forms a lot of times, but there is something else that comes in. And what the implication is, he says that we are the first technological species on this planet. So even though this planet is roughly, I was only a baby when it was born, but it was only 4.6 billion years old. It's taken this long for the atmosphere to form, so that we could have a species of animals, and that animals developed to be able to get a large brain and become technologically savvy and be able to communicate with radio signals. So what we're going to find that Whitmire has concluded that instead of lagging behind our species, we're average, and this is not good news. So Whitmire argues that if we are typical, it follows that species such as ours go extinct soon after attaining a technological knowledge. I don't feel comfortable with that, but that's what. So the Mediocrity Principle, let me step back, going to Wikipedia, is a philosophical notion that if an item is drawn at random from several sets of categories, it's likelier to come from the most numerous category than from any one of the less numerous categories. Okay, so we are typical. The principle has been taken to suggest that there is nothing very unusual about the evolution of the solar system, Earth's history, the evolution of biological complexity, human evolution, or any one nation. Okay, it is heuristic in vain of the Copernican principle and is sometimes used as philosophical statements about the place of humanity. So we are typical. Okay, this would, if you take a sample of, you know, thousands of planets, they would, on average, they would look like us. That's what he's saying. The idea is to assume mediocrity rather than starting with assumption that a phenomena is special, privileged, exceptional, or superior. Okay, interesting. Okay, by the way, there is in the Anastropic Principle, it's a group of principles attempting to determine how statistically probable our observation of the universe are, given that we could only exist in a particular type of universe to start with. Okay, so in other words, scientific observation of the universe would not even be possible if the laws of the universe had been incompatible with the development of sentient life. And proponents of the Anastropic Principle argue that explains why this universe has the age and the fundamental physics constants necessary to accommodate conscious life, since if either had been different, we would not be around to make the observations in the first place. Okay, and anatropic reasoning is often used to deal with the fact that the universe seems to be fine-tuned. Okay, so the argument based on two observations of that he had: we are the first technological species to evolve on Earth, and we are early in our technological development. We're only 100 years old. He could, by the way, he defines technological as biological species that have developed electronic devices that can significantly alter the planet. Okay, the first observations seem to be obvious, but as Whitmer notes in his paper, research believes the Earth should be habitable for animal life at least for a billion years into the future. Okay, so that if for some reason we destroy ourselves, then there should be new life developed, and therefore a new civilization eventually could develop again. So based on how long it took proto-primates to evolve in a technological species, that leaves enough time for it to happen another 23 times. So if we just destroyed ourselves, or one day we just, you know, stopped being around like the dinosaurs, in 65, the dinosaurs were extinct by an asteroid 65 million years ago. And so 65 million years later, we developed. And so if we were wiped out, and another one in 65 or less million years would develop. And so in the life of our planet, there should be another 23 times that technological life should form. And he's saying that that is not going to happen. So on the time scale, there should have been others before us, but there was nothing in the geologic record to indicate that we weren't the first. We leave a heck of fingerprints if we disappeared overnight, okay? And so by Whitmer's definition, we became technological after the Industrial Revolution and the invention of radio, or roughly 100 years ago. And according to this principle of mediocrity, a bell-shaped curve of ages of extinct technology, civilization, universe would put us in the middle of a 95th percentile curve. In other words, technological civilization, millions of years or longer, would be highly atypical. Okay, that what he's saying is, so since we are first, other technological civilizations should also be first. Okay, and the principle of mediocrity allows no second acts. Okay, the implication that he comes up with then is that once species become technological, they flame out and they take the biosphere with them. Okay, I don't feel comfortable, but that's what he comes up with, why we haven't been visited, or put it this way, we haven't been able to communicate. He argues that the principle holds for 2 standard deviations, or in the case, he says that our civilization will last for roughly 200 years, but there is a distribution of this, and he says there's no absolute upper limit, but the ages cannot be less than 0. He doubles the figure and comes up with saying that the high probability out to 2 sigma standard is 500 years, and that it is possible that we could exist for 4,000 years. Okay, the assumption of a bell-shaped curve is not absolutely necessary. Other assumptions give the similar results. Okay, so atypical, there's always the possibility that we are atypical and our species lifespans will fall somewhere outlying the 5% bell curve. If that is the case, we're back to the nugget of wisdom Whitmer taught his students for more than 3 decades, that we're very early on. So the conclusion, and after I do this, I would like to open it up and see what other people have to say about this and what we can say. Our interference regarding the fate of the typical technology species are based on 2 observations and essentially 1 assumption. Okay, the observations are that our technology species is the first such species to evolve on Earth, and we are early in our technology evolution. We're only 100 years old. The assumption is the principle of mediocrity applies to reference class of an extant technology species, and given the assumptions that suggest interference is the typical technology species has a short lifetime and their extinction coincides with the extinction of their planet's biosphere. So he's saying this is the typical end, and so therefore life forms that are technology advanced to be able to communicate with other species only are around for such a short time that the probability of 2 of them interacting with each other is infinitely small. And at that, I thank you for being here. And I would like to talk about this because it has a lot of implications on where we're going and how long we will be around. And are we at the peak of what's our civilization? And it's going to be downhill. Okay, so I'd like to open it up. I'm going to stop sharing screen and I'd like to get other people's comments on this.
Okay, we have 3 questions, and then what I'll do is for anyone that wants to raise their hand, I'll enable your mic after the questions are read through.
Great, great.
Okay, so Bob Ruggiero asks, shouldn't we be looking for intelligent life on Earth first?
Oh, on Earth?
I guess
okay. By the way, it doesn't say we're smart. It says we can communicate with radio waves or electromagnetic waves. So we can communicate at a distance with the technology we have. But it doesn't say we're smart. I really think we have a flaw in terms of we survived and when it was tough, and now we use the id in a bad way. But anyway, but okay on that end. I didn't say we're smart. Okay, I just said we can communicate with radio waves. That's the definition of a technological society or civilization.
Brian Lemley states, except the dinosaurs didn't have a space program.
Right.
and Frank.
Yeah. Go ahead.
No. This is the third. This is the third question. So
yes.
If you have more to add, go ahead.
No, I have no.
Okay. So Frank asks, the implication is that technology leads to societal instability. Are Luddites correct?
No, he doesn't imply that. It doesn't say that the technology leads to destruction. But the question is, it's these. What does lead to the destruction? I mean, by the way, there's a couple papers from this gentleman. One of them was published. The other one is on his website. But he goes into a lot of detail how he comes up with the statistical model that he has and what the lifetimes are. I didn't want to do that because I wanted to have an open discussion, because the implications are that we only have a couple hundred more years of human beings on this planet, and that when we go out, we're going to take everybody down with us, because that's what it's saying. If we destroy the biosphere, that means we take everything out. So that's what's troubling, and so that's what his implication is. The other one, because so far we haven't been in touch with anybody. Maybe the continuation of the more powerful ways of detecting, we will pick up somebody. But at this point, it's since the 1960s. Matter of fact, Arecibo, big telescope in Puerto Rico, was open for a while looking for signals from other civilizations, did not detect anything. So the
All
question is, what that's the only test point we have. We have not, no one has tested us that we could detect it from anybody. And we've tried. Maybe we haven't tried hard enough. But what's the implication? Because what it means, it scares me. It says, we have a couple hundred more years and then poof. And being a physicist, I was always concerned in the 60s and 70s with nuclear weapons, being that they could take out the planet. If you do, you go into a crazy nuclear war, you could destroy the planet. But the other one that I'm seeing now is the climate change. That could be the other one that takes out the planet. So I'm seeing that there's possibilities, and I'm just, are we trapped? So I really like to hear from other people on this. As I say, I didn't go into all the details. Because I didn't think that was important. The important thing is the implications that I see for our future generations. Do we give them? Is there a warning out there that? Is there a way of overriding this? Is there something out that we're saying, that there is a threat? Do people listen to it? I don't know. This pandemic has made me very pessimistic on our being able to join together to fight a silent enemy, so to speak, that can destroy us. And so I'm not sure.
Okay, yeah, great. And so Brian Lemley raised his hand and he wants to ask his question live. So Brian, your question is?
Yeah. Where did Sharma publish his estimate on L, or is how long we have a communicative civilization?
I'm not sure. I have to look on that. The Whitmer published his in the International Journal of Astrobiology in 2019. The paper was first written in 2017, and it took him a little bit to publish it, but it's
well, it had to be peer reviewed.
Yeah, and it's on his website in the form that he submitted it, and then you can actually get it free, a PDF of actually from the International Journal of Astrobiology. And then he has a second paper where some people argued about some of his estimates, and he presented some additional information on a second paper, which is, I'm not sure he submitted for publication, but it's on his website. And there was the original write-up on this was in one of the science magazines, sort of talked about this work, and that's where I picked it up. And then when I started reading it, it was like, whoa. And then I went and read his papers. I didn't get through them all. He starts going into statistical analysis, but I looked at it and said the ramifications are really very paramount to what we're looking at.
Okay, thank you. All right, so Cliff Ashcraft is raising his hand. He'd like to ask his question live.
And please give me, you don't even have to ask questions if you have comments, because I don't have answers.
Well,
all right, Cliff.
I raised my hand because I wanted to join the discussion, but I typed in a question to the Q&A box, and I questioned that the demise of the technological civilization must extinguish the biosphere. I'm looking back at the end of the Permian extinction event, where 95% of all life died, Permian to Triassic boundary. That's bigger than anything I can imagine we could do. yet life survived, and it actually stimulated the evolution of homeothermic organisms, including the mammals of today, mammals and the birds. So
Right.
it's hard to imagine that we could do something so disastrous, whether in atomic warfare or in climate change, that after it wiped us out, everything else would be wiped out too.
If we destroyed our atmosphere, he was saying that it took over 1 billion years for the atmosphere to form. So I think in one of his papers, that's the argument he was talking about on that end, was that it took over 1 billion years for, if we destroyed the atmosphere, for a new atmosphere to form takes quite a long time. Because if you look at development of planet Earth, we didn't start seeing life, animal until about 2.3 billion years into the age of our Earth, because it took quite a while for plant life to develop oxygen in the atmosphere and then animals to form. But maybe plants could become technological. I don't know, but so that's one of the arguments he talks about, that it will take over 1.5 billion years for a new atmosphere to form. That it can, but by that time the Earth is starting to suffer from the sun increasing in temperature. So,
okay, Al.
Yeah, but you're right. But on that end, yes, maybe we'll have one more or two more civilizations on this planet that reach the technological point of radio communications.
All right, so we have two other people that want to join the discussion, but we have a series of questions that started streaming in, so it got really hot. So I want to try to read through some of them before we enable more mics.
Okay.
So Jeremy Carlo asks, an escape hatch. What if they're all around us, but we don't see them because they've taken measures to conceal their identity or use communication methods we can't detect?
That's a possibility. And the question would be, why? And because I thought about that one too. And so why would they want to do that? Why wouldn't they want to communicate? Because if you're a Trekkie, remember if the Star Trek, the Federation would not communicate with a planet until they reached a point where they can travel in space. And at that point, they would uncloak and they would then communicate with that planet, because at that point, that planet can travel away from their planet. And so that would be when they would start to communicate. So he has a point there, but we are at a point where we can leave the planet and we can travel outside of our Earth. And so the Federation should be communicating with us. So the question is, why are they not? Well, maybe, the possibility is that they consider us very dangerous, that we're very aggressive creatures, and they're afraid that if we escape from the solar system and go other places, that will not be good for the Federation.
Oh, well, that's
a good point.
That point reminds me of a book called Roadside Picnic, which is how there's a black market of people that are collecting the tech that's left over when an alien craft lands and takes off right away without even noticing the humans on Earth. So like the pollutants that they left back turn into tech for us to use. It's almost like if you would think that if a civilization would advance so far where they could travel between galaxies, what are we, right? Like we're ants.
Right. And well, remember the Roswell, that Hangar 40, they have this a craft from an alien civilization, and they're slowly learning the technology. They had like Teflon, and they discovered, the aliens had this, and we're slowly releasing this, but the government is keeping it under wraps. So.
Okay, we've got a ton of more questions here. So Bill asks, are we just listening for indications of life, or are we also sending out signals?
The Arecibo sent out signals. So they sent out signals to because that radio telescope actually has the capability of both receiving and sending out high-powered signals. Matter of fact, Arecibo sent out powerful signals that they bounced signals off of Venus and Mercury, I mean, and they were able to measure how fast it rotates. And Venus, I think it was Venus that they did the rotation, how fast it rotates. So they were able to bounce signals off the surface of Venus because and then detect the bounce signals from their antenna. But they did send out signals trying to communicate, sending out I think they sent out pi 3.1415, so that people would know that it wasn't completely random, and that any civilization pi would be a very important number. And so if they detected that number, they realized that we were mathematically attuned to be able to do geometry. So we'd be that advanced. So they did send out signals. I'm not sure anyone else has, because you really need a powerful antenna. And
Okay, so Nancy Toscas has been waiting patiently. Nancy, I've enabled your mic for your questions and comments.
Okay, Al, the equation that you showed, that only applies to the number of potential civilizations within the Milky Way galaxy?
right. And the problem is that, you know, the signals coming from another galaxy would be probably so weak that we really don't have the technology to pick up a signal from another galaxy. So the feeling is that within a star within our galaxy, we should be able to detect a artificially generated signal from a planet, where from another galaxy, it's at this point we don't have the technology to do that. But maybe in the future we will have, you know, bigger radio telescopes with more sensitive electronics that could detect signals from another planet on another star in another galaxy, as we did in, Star Wars? That took place in another galaxy.
Can I ask one more question?
Sure, please.
A hypothetical question. So if we were on one edge of the Milky Way galaxy and sent out radio wave, would intelligent life on the other edge of the Milky Way galaxy be able to receive it? It would carry that far, I guess, and then you have the black hole in between. I don't know what happens.
Yeah. Well, here's the thing, though, is that if we started sending out radio waves 100 years ago, Arecibo didn't do it until the 50s and 60s, but it travels at the speed of light. So if somebody is 100 light years away from us, they haven't detected our signal yet.
And the signal would actually just keep going. It never fades out.
Right, it would get weaker and weaker as it gets farther away by the distance squared, but it could travel to the edge of our galaxy. It would be a very weak signal, but remember the size of our galaxy is 100,000 light years, so it would take that long for it to reach the other side of the galaxy. And the same way, if someone on the other side of the galaxy, edge of the galaxy, we're not in the center of the galaxy, and we're not in the edge. We're about 2/3 out from the center of the galaxy, but you know, it would take that long for that light to reach us. But we should be able to, we could detect it. It would, the advantage of using that kind of signal is that the civilization could be dead on that planet, on that star that's, 10,000 light years away from us, but its radio waves has reached us. And so it reaches us, and we're getting the signal from that star 10,000 years ago, but we at least got a signal that said at some point in time that there was life on that planet that was technology advanced that could produce radio waves. And so far, we have not gotten anything in that nature. Most of these stuff we've been looking at has been within like 1,000 light years from us, because we figured that's the best chance of getting a strong signal. But it would be nice to get a couple signals to say yes, there was life maybe they're not there now, but at least there is life on another planet, advanced. By the way, it doesn't say anything that, you could have life forms on a planet, but they're not technological, and then might not be able to become technological for some reason. That they're just, they're amoeba or whatever, single cell animals that existed. I mean, one of the things is that we believe life was on Mars at some point in its history, a couple billion years ago, because Mars most likely had water on its surface, and most likely life developed, maybe very simple life, but there was life, but it wasn't technological, and that couldn't communicate. So far, we've been not successful.
We got one question that came in as a comment on Facebook.
Okay.
It's from William Whitehead. Al, has any radio signal originating from this planet ever reached the nearest star?
I can't answer that question because I haven't been on the nearest star. It should be able to travel that far. It would be very weak, but with the proper electronics and a large size radio telescope, you should be able to pick up the signal, possibly.
All right. Now, Jim has been waiting a while too. So here he is. Too long a conversation. We are at or past the tipping point of an unstable equilibrium as albedo decreases, as polar ice melts. I guess that was a comment.
By the way, I believe you're right, because I believe that, even though a lot of people are saying the tipping point is going to be in 8 to 10 years, I really feel that we are at we passed the tipping point, and that we're going to have to look.
It is warmer than our ancestors were used to, but
all right,
yeah, I can't say anything more than that. I worry about that, but I really feel that we've reached the tipping point and past it.
John Sickles states, I'm as pessimistic about our future as the next guy, but it seems to me there are too many assumptions into all this reasoning.
Well, the problem is he has a data point of 1. Us. Okay, are we really typical that we are a planet with an extremely large moon? You realize the probability of a planet having a moon as big as our moon. If you look at all the other planets in our solar system, their moons are on their relative size are much smaller. I mean, Jupiter has a bigger moon than us, but it's 11 times bigger than us. Okay, so we have a humongous moon that has kept our planet in its position, locked in, so it doesn't rotate very rapidly around its precession point. Remember that our planet's tilted at 23.5 degrees as it goes around the sun, and that tilt precesses, but it does it slowly because of the moon. So, and the moon has caused large tides, and because of large tides, animals got caught off of being in the ocean because that's where life formed. And so animals ended up being trapped on land and then got used to being on land and eventually stayed on land. Is that typical? I don't know. I mean, so maybe we are just atypical and not typical. But what Whitmer is saying is, if you use the principle of mediocrity, that if you put your hand into a bag of objects, you pick up something which is on the average, the most of anything there. So if you have a bag of balls, and most of the balls are blue, but you have some yellow and some red, and when you put your hand in, mediocrity says you most likely when you take your hand out, the ball you get is blue because that's most of the balls in the bag. And so he's saying we have one case for a civilization that is advanced technology-wise, and that's us. So we're typical. And if you assume we're typical and not atypical, then this is what he comes up with. Okay, so that's what his paper is all about. If you assume we're typical, then this is what his conclusion is. But maybe we are still atypical, and the probability of life forming and advancing to this state is so small, and that is why we have not observed it.
Right. Wow. Okay. So Cliff and Neil have a series of comments. Cliff adds,
Please.
no warp drive yet. No world government yet. And then Neil concurs. We haven't developed faster than light speed yet. And then Cliff states
Right.
137. I don't know the meaning of 137. Cliff, care to elaborate?
137
137?
is reciprocal of the hyperfine constant. And if we communicated that, they would know we were smart in physics.
Oh, okay. I'm not sure I'm not sure they were sending that number. I thought they were using pi, but I could be wrong. Arecibo, I know, had the most powerful transmission capability for radio waves, and so I know they transmitted, but maybe they did send the fine constant 137.
All right. So Brian had his hand up. So Brian, your mic is hot. Brian McGinnis.
No, his mic is off. Still off. I see it.
It's okay. All right. Well, all right. Let's move on. And John.
No, he just turned it on.
Okay.
He just turned it on.
I just want to be part of the conversation and stay online. That's all I raised a hand for.
Oh, okay. All right. Stephen, now your mic is hot.
Can
No,
you
it
hear me?
isn't. Oh, here it is. Yep. Yes, we can.
Yeah, I guess it's a comment as well as a question. Obviously, humans can destroy themselves pretty fast by purpose or by accident. But still, the population is growing. One good lecture I listened to, and I'm sure Dr. Mary Lou West, she was there. One of the scientists, and I can't remember her name, pointed out that our biggest problem would be actually our gross domestic product, how fast we're growing, as well as the other nations, by utilizing up our resources. And of course, do we have the ability to reach out and get more? So in her estimate, I believe the human race would last 100 million years. That was the limit. Now, how she arrived at that, I'm not sure. But on the other hand, I believe we've learned a lot about these extremophiles that can survive in environments outside our biosphere. So that's a good point for life to continue.
But the question will be, will that life develop into an advanced technology? It's possible. It's a good point. Is it possible? I mean, from the reason I wanted to do this is because it opens up a lot of questions. Because as I say, the one postulate that I've had in the past was that we're very atypical, and that's why we haven't obtained, seen communications with other advanced civilizations. And this paper, when I saw this talking about this, it was a different approach of why we haven't observed this. Because what he's saying is, it's not just us, but every civilization that forms will destroy itself in a short period of time and take out the planet with it in terms of its biosphere. Is that really possible? I mean, is there a quirk in that says that, isn't there a chance that there may be a civilization that develops that, as you say, could, with the GNP, could survive for 100 million years? And at that point, they would know how to reuse things, and so that they would recycle everything that they have, and so they could go for another 100 million years.
Yeah, another point about communicating with other life forms. As far as we know, a photon can travel forever if it's not inhibited some way. But when you generate a photon that can travel that distance and time, you're doing it from a star. which is a tremendous amount of power that we can't even come close to duplicating in the small little telescope that we've tried to generate.
Right.
So I would think that that attempt would be extremely limited.
Matter of fact, that's why they're saying most likely we're looking at communications within less than 1,000 light years from us, which is not anywhere near the size of our galaxy.
And in a limited directions as well.
Limited directions. And, you know, one of the plans, I really think there should be plans to set up a city on the moon. And one of the plans was to put up telescopes on the moon. And you could, on the moon, you could put a humongous radio telescope, which could not only detect very weak signals, but actually broadcast some very strong signals and improve our range of looking for other technology species, you know, than we can do now. And you're right, as you really need, you know, your signal just falls off by this. The power of the signal falls by the square of the radius, how far away you are, the square of the distance. So you know, when you go, you know, to 2,000 light years away from us, you're 1/4 as strong a signal as at 1,000, and so the signal gets so weak that you really need very, very, very good detectors, or very, you know, and that means large antennas with very good electronics. And so, you know, maybe we don't, you know, maybe there are someone just beyond the 1,000 or whatever it is limit, and their signal is so weak we can't detect that they're there, and our signals are not strong enough for them to detect us. Or maybe they did detect us. Maybe they have detected the signals from our SIBO, and they go, hey, you know, Seymour, there is life out there. The equation that you got that said that we're not going to only live for a couple hundred years is wrong, because there's other life out there. But we can't tell them, because if we send the signal back to them, it's going to take 2,000 years.
All right, so Cliff is virtually waving his hand, although
Okay.
your mic is hot, Cliff, so you could chime in. There's nothing stopping you.
I have a kind of an argument against the principle of mediocrity, and that has to do with time. Chemistry is important. And as Carl Sagan said, we are star stuff. And
Yep.
the star stuff that we are made of is probably gone through the nuclear furnaces of the supernova 4 or 5 times, maybe 7 times. And the result of that has been a significant concentration of heavy elements in the planets that make up the solar system, and in particular the Earth. And these heavy elements are critical from the point of view of the catalysis of biochemical reactions. Is it possible that we are at a very non-mediocre point in time where sufficient planetary systems have evolved containing enough heavy elements to allow things like hemoglobin to exist, and that we may be among the first, and because we're the first and there's lots of other firsts, we just haven't had enough time for our radio signals to reach each other yet.
Absolutely. Right.
All right, so John Sickle also has his hand up to join the conversation, but before I enable your mic, I'm going to read your first question just to set the context. John asks, how do we know aliens want to communicate? How do we know they haven't already by some other means we haven't evolved to yet? Why do we think they'll be so much like us that we'd recognize communication? Do we really need silence from aliens to understand we have to change our ways? So John, with that, I'll enable your mic and you can unmute yourself.
I just wanted to add.
Yeah, go ahead.
Go ahead, Al.
No, you go ahead.
I was going to say, the issue I have with the principle of mediocrity is that with regard to alien life and intelligence, is there really even such a thing as typical? What if every ball in the bag that we're dipping our hand into is a different color?
Mm-hmm.
Easier
Right.
analogy.
Yes,
Or,
you're right.
or let's say half of them are red and half of them are blue. Which one are we, to be typical?
Right. I mean, he has an interesting approach, but the problem is we have one example. I mean, if we had 10 examples, we could say, okay, this is typical or not typical, but we have one example, us. So how, excuse me,
I
so
mean,
how typical, so are we typical or are we atypical? It's a toss of a coin, almost to say. And as
but
and
again,
as Cliff said, it's taken us a certain period of time for enough of the important elements that make us capable of having a advanced life form as us in terms of the heavy metals, that maybe the universe being only 14 billion years, only about 5 billion years ago was that possible, that planets forming only 5 billion years ago could have the potential of making an advanced life form like us. And so we're all early, and their signals they sent out signals, we send out signals, but we haven't gotten to them yet because they're too far away from us.
All right, so we've got so John also has two other questions in the hopper, but I'm going to read Stephen Cosma's question. Don't direction and frequency need to be considered in the challenging task of searching for signals?
Yes. So when they send out signals, the signals are sent out in a very particular direction, and so you really have to spend a lot of time if you want to send it out in all directions. And I'm not sure how Arecibo probably communicated sending out signals as the Earth rotated, because remember it's a fixed antenna, and so they can do some adjustment, but it's not a full steerable antenna. So they sent out signals, but as the Earth rotated, they sent out different places in the sky, but most likely they didn't cover everywhere in the sky. So there's another problem, that we could have missed sending it out to an area in the sky that has a planet that was communicating or could communicate.
All right, great.
Agree.
All right, Jim is the last question in a hopper, and then Mary Lou West is raising her hand to join the conversation. So Jim asks, there is work to detect signature of technology in exoplanet atmospheric spectra, period.
Yeah. I mean, we're looking at we almost have the technology whether we could say that it's possible that there's a life form on it. But remember, this SETI is different than looking for a life form on a planet. SETI is looking for technology advanced life forms, which is a more even restricted measurement. So the looking for exoplanets where they're saying, oh, that atmosphere has oxygen, which means it's chance. I don't know if they have definitely put that yet, but to have the technology to say, yes, that planet has oxygen in its atmosphere at 22%, like the Earth. Therefore, there is a high probability there's life on that planet. Okay, so that's one end of it that says there's life on the planet. But to say that there's life on the planet that can generate electromagnetic signals so that it could send out radio or light waves to into space and communicate that way is a much more difficult step. So you could have amoeba, but the question is, we want something more advanced than that, and that's a smaller probability.
Mary Lou, your mic is hot. You can.
Okay, so I think it's interesting. Two things about this. I think in this discussion, the really critical step is the communication step, second from the last one. That's the really tough one. And on Earth, we have at least one other variety of intelligence that developed separate from humans, or a lot of people think so, and that's the dolphins.
Yes.
But they're the water, and they may be intelligent, and they may sing and talk to each other and write poetry, but they cannot make a radio transmitter because you can't have fire underwater, and you can't do metals. So maybe this says that there are not very many planets that have a lot of dry land. We don't have very much dry land. It's less than half of the planet's surface. So maybe most of them don't. And that would really cut down on technology for communication. And the other one, which I really liked, which I had never heard before from Cliff, but I'd like to restate it. Maybe you need a planet far enough along in the universe so that we have the heavy metals, particularly neodymium. We need that to make those little magnets that are all over these radio transmitters. Don't have any neodymium, you're not going to have any communications. I don't know.
Yeah.
Or I like the one that Jeremy said, they are transmitting on some other type of waves that we haven't discovered yet. So we think about, you know, if you go to, I don't know, the Amazon jungle or somewhere where there's not a technological civilization very much, and you walk around with a cell phone, you're texting people all the time. They have no idea that those signals are going through the air near them. They don't hear them at all. There's nothing here. And yet here we are communicating right past their ears.
I think we're pretty good in, you know, in radio waves, but maybe there is another wave but that we haven't found, but I'm not sure about that one. Or maybe they're doing it at ultra high gamma ray frequencies, who knows?
All right, Charlie Real says, in response to warp drive, in Star Trek TNG, they normally do not contact other civilizations that do not have warp drive. Maybe other life may not contact us for the same reason.
That could be.
All right, and Cliff adds, look to the center of the galaxy, more generations of stars evolved there, more heavy elements.
That's a good one. I like that.
Yeah. Well,
Where to look? What do you say?
Towards the center of the galaxy.
Yes, yes.
All right. So we got a couple comments in there. I think the only one that didn't really make it out there was Isabel's comment, which had to do with our evolution. I think that stupidity is the thing that is going to eliminate us. So that was the comment from the chat room. You know, I do have one thought here is that maybe some of these advanced civilizations, their science and the physics that they've evolved detected other dimensions that we haven't yet. So maybe that's where they're at and we can't even see it.
To leave on a note, by the way, when the first test of the atomic bomb, the scientists could not guarantee that the chain reaction would spread into the atmosphere and we would destroy the Earth. So there was that little bit of worry that when they set that bomb off, that we'd take out the whole planet. That was a sort of hidden in when they detonated the first bomb. But we didn't do it then. But that was the point, if you think about it, when we really, for the first time, could destroy life on the planet in a massive way. What I found interesting is that if you look at the history of World War I, Europe was fighting the most advanced civilizations on the planet. And I'll put in quotes if that's advanced, but technology-wise, they were very advanced. They were throwing everything at each other in almost in a self-destruct mode, but effectively they couldn't destroy the planet. But once we got an atomic bomb, that's when the technology reached a point where we could destroy ourselves and even the atmosphere in a way. So is that every civilization, does they reach a point when they get that kind of technology, is that when it becomes dangerous? And what is in their DNA that says that the general good is more important and they can overcome what Freud called the id, which is self-destructive?
All right. Okay, Jeremy raised his hand to join the conversation. Jeremy, your
Great.
mic is hot.
Yeah, just getting back into this idea that they're communicating in ways that we can't detect. I mean, we don't even have to go into crazy stuff like extra dimensions. I mean, if they're just using some spread spectrum technique, we wouldn't be able to figure it out because it's spread out over a bunch of frequencies. Or maybe they could be using something at 22 gigahertz or something like that that's strongly absorbed by the atmosphere. Travels well through space, but you can't detect it from the ground. I mean, that would be a possibility, or maybe they're at terahertz frequencies that we're not even really listening.
Right.
I mean, one idea that comes to my mind is, let's say that there were radio signals from alien civilization passing by the Earth. Would we even detect it? Because, unless they're doing 1420 megahertz, which is where we're listening, we're probably not even going to notice it, especially if it's a weak signal. It's
Right.
just a little bit of extra static on your TV. It's just, a little bit of extra noise, when you're listening to the radio, or maybe just spread out over spectral space that, unless you have a detector that's modulating with the right function, you're not going to see anything at all.
Matter of fact, the technology of spread spectrum and frequency hopping is used, for communications that are protected so that your enemy can't pick you up. And so they could assume that that's the communications that people use, and things are bouncing off at different frequencies, and you just don't know what it is. You're right.
Yeah.
So one of the things I wanted to do with this talk, though, was also is on the 29th, that talk that our club can join in on. I'm curious, what is the latest that SETI is doing to improve their chances of detecting signals from other life forms? Are they doing some of these things to look at more advanced signaling and at different frequencies and different techniques to look for this? And maybe we'll have to wait until we get our city on the moon that has a nice big radio telescope that can do better than what we do on Earth, that, in terms of detecting some signals.
Yeah, the far side of the moon would be great for reducing noise level. But I mean, spread spectrum is not even just for secrecy. It's used to basically beat noise. Our cell phones are spread spectrum.
Right. Yep.
So it's not even necessarily that they're being secretive. It's that they're trying to avoid noise sources by spreading out over a frequency range.
But it makes it very hard then for your detector, because you're going to have to, the number of possibilities just goes up exponentially.
Yeah, but if they know who they're communicating with and they share the code, then it's easy.
Right.
So Al, this conversation is still going. We've got more questions streaming in. We've got more cues in, but we do have the stream going live on Facebook. So what we'll do is I'm going to turn it back over to Mary. We'll let her we'll let her close us up, and then we'll shut this Facebook stream down and continue the conversation in the social hour.
Great.
Yeah, Al, I wanted to thank you very much. This has been really very interesting, and I'm so glad with all this participation by our members and even somebody from Facebook chiming in too. So thank you again, Al. And I just want to remind everybody to join us every Friday night at 8 p.m. as we continue these weekly presentations. Next week, our presentation is Fake News of the Solar System by Al Witskell. So I hope everybody joins in then. And thank you for joining in tonight, and wishing everyone clear skies.